Okay, so I went to the physics of baseball lecture done by Mr. Alan M. Nathan. Um, and he didn't talk a lot about like the actual equations between like the ball and obviously physics, but or in the bat as well. But he did. Talked a lot about like the concepts that you would deal with instead of going like let's present something, that a lot of people wouldn't even understand. Let's talk about like what it actually means. So he talked about the dynamics of the ball and bat collision, like how the bat works, and like what's better, wood versus aluminum, and then the flight of the baseball, like the drag, lift, and all that, and like the fancy techniques that some people use. So the basic thing is you have a very large force acting in a short time period. So like approximately like 8,000 pounds in under 1 millisecond. So you have a lot of energy lost. And then you can see how like the bat will like slow down. Sometimes after like colliding with the ball, and that bat meters a lot. He said this a lot during the lecture that you can observe a lot by watching. So a lot of what he did, he would show us through slow motion videos, which was extremely cool to see. And then the batted ball speed. So what determines this? Which is the pitch speed, the bat speed, and then the collision efficiency, which is a property of the ball and the bat together. And he came up with the equation for it, which is Q V pitch plus, in parentheses, 1 plus Q times V bat. And the typical numbers you're going to get from that for Q is 0. 0.2. And the velocity of the bat matters a lot more than the pitch, he said. So that because for each miles per hour of bat speed, it's approximately 6 feet, but for each mile per hour or pitch speed, it's approximately 1 foot. That's a big difference there. So your coefficient, your collision efficiency, though, depends on your coefficient of restitution, and your the weight like of the bat. This has to do with the moment of inertia. Bat speed depends on the weight and the moment of inertia of the bat as well. So the coefficient of restitution, though, is the bounciness of the ball, which is approximately 1/2 for a baseball, because it bounces to 1/4 of its initial height, and you get 3/4 the energy loss. So the bats matters like a lot. Okay, and then he goes on to talk about the vibrations and the sweet spot. So the sweet spot, there's an exact spot in the ball, I meant in the bat, that uh, sorry, catching up with my notes here. But when you don't hit the bat in the sweet spot, the vibrations can cause the ball to lose energy, and thus lose speed. And this, like the sweet spot has the lowest frequency. So and because like when you hit like inside or outside of that, you can actually see, if you watch in slow motion, you can actually see like the bat like feeling the wave in the from that. Um, but if you a bat struck like at the handle, he talked about this as like just a little bit of an aside. That a curious feature is the bat struck at a barrel, and the handle only moves like after a noticeable delay, and when reflected, the reflected wave reaches the barrel, like it's just the collision's over. Um, but anyways, back to the sweet spot of the barrel. If the ball hits inside of the sweet spot, it shatters toward the batter. But if you hit outside, then it's gonna shatter away from the batter. So now to aluminum and wood, which is better. Because of the lower moment of inertia, the aluminum bat is better. You get a higher bat speed, so thus lower collision efficiency, which is a good thing. And you also get something called the trampoline effect. And this was when the ball and the bat mutually compress. So the net result is that the ball bat coefficient of restitution is enhanced. And so, yeah. So because of the things you can do, with the ball and the bat, because of the lower moment of inertia, you can make. But when they first started, working on this and figuring this out, you can make a ball go really far just by changing some of the stuff about the bat. So because of this, the NCAA has started regulating. Okay, so now on to baseball trajectories. Um, so forces on a spinning baseball. Look, the ball is spinning, going around like this. Then the velocity. Okay, the ball's still spinning. You got a velocity in this direction. You got a Magnus force in this direction. You got a drag in this direction, and you got a gravity force straight down. And the drag is going to slow the ball down, and then the Magnus plus the gravity deflect the ball from the straight line. So, and he also talked about, how, like in Physics 1, a lot of the stuff we dealt with was perfect. Like, because there was no drag or no air resistance, which is basically the same thing. So, like, but this is, we're obviously not in a drag-free world. So, this affects how the baseball, uh, works. And so now and they also they've started doing a lot of research on but about like how the ball spins and how this affects how far it goes and stuff. So they've even put like high tech cameras up to try to determine how like pitchers do what they do. And then he talked about one particular pitcher, Mariano Rivera, and why he was so good. And it's like he was consistently pitched to one different spot, and that like so he would always be a little bit like, here's the batter and here's your the box. He'd always pitched a little bit on the inside, and like how he consistently did this is though he had a lot of control over the ball and command as well, so he could get the well located strike, because he's just enough in that they're not gonna call it an inside ball, but like they could have hit that, and this is just because he consistently did this. Um, so a lot of another thing about a ball is the spin on the ball, and sometimes this can different spins do different things. So this is where he talked about several different batters and where they a lot of times pitched. So, but also when a ball is hit, okay, it's still like you're looking at the friction and the spin when it hits bat, and that determines a lot of exactly how far it's going to go too. So okay, the ball's traveling in this direction. It hits the bat, and it's got a normal force this way, and it's got friction down. The ball, like that's a big deal. Okay, so and he talked about knuckleball movement, uh which is completely unpredictable because there's barely spinning, because there's so little Magnus force. And he talked about like foul balls and how that balls hit to the left, right, break toward the foul line. And that top spins give tricky bounces infield. Then a backspin keeps the fly ball in the air longer. And then tricky pop-ups to infield. And that pretty much concludes everything like he talked about So, all right.